In this lecture, we're going to continue our discussion of reactions of ethers with hydrohalic acids like HBr and HI. I guess HCl could still apply, but it's Cl is just not that good of a nucleophile. But I want to look at some interesting, some kind of interesting things to consider. And so the first one will be phenyl ethers. Let me get the normal pen. So phenyl ethers cannot react at the benzene side. Okay, so let's remind ourselves what a phenyl group is. So a phenyl group is this. So it's just a benzene ring hanging off of a molecule. So that's phenyl. And so if we had ethyl phenyl ether and we reacted this with HBr, what I'm sort of suggesting is that the Br cannot react on the phenyl side. So this side is no reaction with Br minus. And what that means is that the only two products we'll see in this unsymmetric ether are phenyl alcohol, or phenol is what it's called. Don't worry about that nomenclature right now. And then bromoethane. So these are the only two products that can be formed. So why is a good question. Specifically, why can't phenyl react with a nucleophile? Very good question. And so the reason why is because the carbon being attacked must be sp3 hybridized. And what that means is that it can only have single bonds. Okay, now if we look in more detail at our phenyl ether, what I'm saying is that if we, let's put the H plus on the oxygen. So if we were to let Br attack the molecule, it has two possible routes. We talked about this before. We have a left side route and a right side route. So the left side route, this is okay. But the right side route would attack this carbon, and that carbon is sp2 hybridized. That is, if we kind of zoom in on it. Okay, so we have these three groups attached. So it has three things. It doesn't have a lone pair. So we need an S plus a P plus another P. That equals sp2 hybridization state. And we would just know that it's not sp3 because it has double bonds attached to it. We can only have single bonds attached to the carbon that's being attacked by the halogen in this reaction. The specific reason why has to do with the SN2 reaction. If you recall, in the SN2 reaction, we required backside attack with inversion of configuration and that sort of thing between the nucleophile and the electrophile. We can't do backside attack when the carbon is sp2 hybridized. This also works for SP and sp2, or I guess also doesn't work for other sp2 and then sp hybridized carbons, but those are too unstable to make. It's really hard to make an ether with an alkene directly attached to that unless the alkene is part of a benzene ring, which is inherently stable. So this is sort of a sort of one-off example. And if you had diphenyl ether and you tried to react it with HI, on both the left side and the right side, we've got sp2 hybridized carbons, and so we would not see a reaction on either side. So I'm going to put NR for no reaction. Okay, so that's phenyl ethers. The next one I want to look at are T-butyl ethers. So when I put the T superscripted and on the left side, that's referring to tert-Butyl. or this sort of chicken foot hanging off of the rest of the molecule. So if we have a tert-Butyl ether, something interesting happens. That is, if we react this with some sort of H+, and it could be any source, it doesn't matter what the source is, what we typically see are only two products. We see the alcohol form along with this unusual alkene. And the alkene is called isobutylene. If you count, it does have 4 carbons attached to it, and it's an isomer of butylene. So ene meaning alkene, iso because it's an isomer of butane, and but because it's got 4 carbons like in butane. And so this is actually a gas. Isobutylene is a gas that can float away to some appreciable degree, and we get an alcohol. So it's important to note, though, that we could have any source of H+. Really, any strong acid will do. Now, what I want to do is take a second to go through this mechanism before we worry a little bit about how these products are different from the products that we've seen with other acid reactions on ethers. Okay, so let's go through the mechanism of this. We've got a tert-Butyl ether, and I don't care what the other side is. It's any carbon group. Okay, it can be a phenyl, it can be whatever we need it to be. And we're going to have H+, because H+, and it's going to be considered in our first step, because H+ is a subatomic particle, so it will react before anything else in the reaction mixture. And it will engage the lone pair of electrons on the ether. Specifically, those lone pair electrons will do the attacking, and that will give rise to this protonated ether intermediate. It has a positive charge on the oxygen. Okay, now instead of waiting around for a nucleophile to do some attacking, right, we would typically have some nucleophile come in and do the attacking. That's not going to happen in this case because the tert-Butyl group, the chicken foot that's hanging off of the molecule, was so prone to simply falling off and walking away. If it falls off and walks away, it's going to dump the electrons onto the oxygen so that the carbon atom now has a positive charge and the oxygen now is neutral. If you recall, in mechanisms, we have to balance the charge on either side of the arrow. So we let this walk away. Now what this forms is a very stable tertiary carbocation. It's highly stable because it's very substituted. It has the maximum possible groups on the carbon atom that has a positive charge. So it's a tertiary carbocation. If you want to figure out why, look at the carbon with the positive charge. How many things does it have attached to it? 1, 2, 3. So we put a tertiary label on it, which we label as a 3 with a degree symbol around it. So because the very stable tertiary carbocation can be formed, it does form faster than the nucleophile can engage the carbon atom. And it turns out that for the most part, depending on what acid that you have, you will see the formation of isobutylene, at least in some appreciable amount, where a hydrogen adjacent to that positive charge simply falls off to give rise to this alkene. We actually looked at this a few lectures ago in the sort of basic mechanism review. This is an E1 reaction. That is, we do an elimination from a carbocation intermediate, and we've already generated our alcohol. So the alcohol has been formed. The isobutylene has now been formed. The pathway is an E1 pathway. So we treat the tert-Butyl ether with acid, and it doesn't matter what's on the right side. On the left side, we always have a tert-Butyl group, or they could be flipped. Anytime you see a tert-Butyl group, you've got a tert-Butyl ether, and this principle will apply. You'll form an alcohol selectively on one side, and then on the opposite side, you'll form isobutylene. I mean, maybe it could do a subsequent reaction that we could talk about in the future, but let's not worry about that. We form that highly stable carbocation intermediate that gives rise to isobutylene and our alcohol. Now, because this is a very controlled process, okay, that is we get one alcohol and one alkene. This approach proves to be reliable. And in the future, we could talk about something called a protecting group, where this is a nice strategy for the protection of alcohols. Maybe we don't want the OH to react with the base in some steps. So what we do is we mask that OH as a tert-Butyl ether, and we can easily remove the mask by treating that tert-Butyl ether with hydrogen. The other thing I want to emphasize about this step is the reaction between a tert-Butyl ether and acid is catalytic. Now, what does that mean? It's catalytic in H+, it turns out. Let's look at the mechanism again, but let's pick on a specific example. Let's say I've got, let's go ahead, let's tie a phenyl ether on a tert-Butyl ether. This will be a pretty streamlined reaction. We're going to react this with H2SO4. Again, any acid source will work. We don't need the Br minus, the I minus, the Cl minus, the whatever minus to serve as a nucleophile, because the tert-Butyl group is simply going to fall off. Now, when we see a strong acid like this, I immediately, when I'm considering a mechanism, cross it out and replace it with H+, because I know that's what the purpose of the addition of a strong acid is. I'm going to let the oxygen engage that strong acid to give us a protonated ether. I know I've got the top lone pair being shown attacking the hydrogen, but I'm just going to let the hydrogen sit below because it gets a nicer picture. Doesn't matter where I put it, but this is probably more representative. Still be tetrahedral in geometry because of the lone pair. Okay, neither here nor there. So we protonate the ether. At this point, we let the tert-Butyl group fall away through a heterolysis reaction. The oxygen is going to absorb the electrons, leaving behind a positive charge electron hole on the carbon atom. That's going to give rise to phenyl alcohol. Plus our tert-Butyl cation, which is highly stable. And we're just going to lose an adjacent hydrogen. Any one of the 9 hydrogens can fall off to give rise to this product. Now, in that last step, okay, the alcohol is done. The isobutylene is done. But if you look, we actually lost a hydrogen. That is, this hydrogen loses its electrons that it's sharing with the carbon as the carbon uses those to form a carbon-carbon double bond. As a result, the hydrogen is released as none other than H+. Anytime we have a reagent that is both a starting material and a product, that reagent is a catalyst. If you recall from Organic Chemistry 1, I tried to emphasize that in many advanced catalytic systems, the atoms that go in will be the same as the atoms that go out. But that's not what defines a catalyst. That's what defines this little heuristic: the catalysts are never consumed. Now, I tried to emphasize that that's not the most precise definition of a catalyst. A catalyst is both a starting material and a product of the reaction. That's important here because the H+ is both a starting material and a product of the reaction, but the H+ that went in, that is up here at this point in the mechanism, the H+ that went in is not the same as the H+ that went out. The H+ that went in is now part of the alcohol, whereas the H+, that came out was part of the T-butyl ether. So we start with an H+, we get an H+ out. The H+ is catalytic, but the H+ we put in is not the same one that got out. The H+ that we put in was consumed. It was just that another H+ was regenerated to continue on another catalytic cycle. Now, is that just semantics? Maybe. I'm still kind of weighing that in my mind. But some people are using those semantics to justify not calling this a catalyzed reaction, to not specify that this has been promoted by an H plus catalyst. That bothers me a little bit. They like to say different things like this is an acid promoted reaction, not an acid catalyzed reaction. I don't know. I mean, the reality is in the early experiments on catalysis, when acid catalyzed reactions were very first discovered, chemists had to tackle with the mysteries of adding less and less sulfuric acid to reaction mixtures and seeing more and more product go in. That's because the H plus from the sulfuric acid was a catalyst, and adding less and less promoted fewer and fewer side reaction pathways. And just how important catalysis is, I don't think we want to start taking away opportunities to introduce catalyzed reactions. So I don't believe we should call these things acid promoted. I would say acid catalyzed, but maybe you disagree. Okay, I've laid out my arguments. Okay, that'll do it for this lecture.